Good evening. Today we'll be talking about the GIS data models. So as a outcome of this, or basically learning objective under this particular lecture, is that the people who are not familiar with GIS, so they should first get to know that what are the important data structure which is being used in GIS. Along with that, how the spatial relationship are being represented in GIS. Then we'll also look into the few basic uh, representation of data models, which is present in GIS world. Continuation to that is basically understanding or differentiating between raster and vector data sets, and as well as understanding what are the limitations or the error if we take data format from one systems to the another systems. Then we'll also look into a few steps, the few standards which is present in data, which is being used in GIS data model representations currently, and as well as few GIS data format which is currently existing and which is being used widely. So at the end of this course, basically the participants would be able to understand that why do they need GIS data structures, what are the difference between raster and vector data sets, then what are the different data sets to represent the spatial relationship, especially the topological relationship in which data sets the topological relationship can be presented. Then we'll also look into that how the data conversions affects the GIS analysis, and this is one of the important aspects whenever we are carrying out the analysis. So this particular understanding is also an important part for doing any kind of GIS analysis, as well as we'll also look into the detail of existing data structures which is being used currently, and what are the basics geospatial standard which is currently being used in representation of different GIS data sets. So let's first understand what exactly is the GIS analysis. So generally we are familiar with the problems where we have to find out a route from place 1 to place 2. So in this case, the example is that we are at Institute of Remote Sensing and we want to go one of the prominent locations in Dehradun, that is called Clock Tower. And anybody who is coming to Dehradun, probably, or maybe in IIRS, he may be interested in going to a clock tower for visiting the visiting the different marketplaces which is nearby in the clock towers. So this is basically the very routine, mundane requirement for anyone who is coming to IIRS. So in this case, the general anyone who is new to this place will be needing some informations to get the solution that how he or she can reach from Indian Institute of Remote Sensing to basically the clock tower. So this can be considered as a GIS requirement, and on the basis of that we can find out or execute few GIS based analysis which is called a shortest path route finding. Then there can be a lot of other parameters also. So based on that we can say that we have to follow a particular route path and then we can reach the clock tower from IIRS. So this particular requirement requires a kind of interactions with the GIS tools. So generally, if you see the information which is present on Earth, which is actually a part of reality, there are a lot of cluttered information. Like in this a piece of information which is collected from from satellite imagery, you can see there are a lot of different places being marked. There are houses, there are buildings, there are schools, colleges, road, lot of trees. So in reality, the information which is present on the Earth surfaces are quite complex. But to carry out the analysis, we need only a few selected information out of all these detailed level of information which is present on the Earth. So this transformations require some kind of data selections and as well as arrangement of those data sets so that we can carry out the problem statement which was given earlier. So these conversions, once we are able to do it, then only we can do a further GIS analysis. So in general, if I say that GIS systems basically takes very routine, mundane questions like just putting the informations in your Google map or maybe in any other GIS tool-based systems, where you simply say, I want to go from place A to place B. And at the end, it gives you a simple answer in form of map, maybe a set of instructions, written instructions, or maybe a verbal instructions to or anyone who is asking that particular questions. But in between, there are a lot of intermediate steps which needs to be followed so that these queries can be answered by any kind of computer systems or a machine in general. So that requires a kind of conversion of any kind of GIS requirements in related GIS questions and then executing a specific process models. For example, to find out a route from one place to the another place, we need to do some kind of networking analysis, look for specific algorithms, and then find out the representations of outcome of those results as a solution GIS solutions, which again gets answered, which gets represented to end users in form of maps or maybe in form of some verbal instructions, and that is how the answer gets generated from GIS systems to the human consumable format. So for doing this, whenever we convert the GIS questions or carrying out the GIS analysis, we need to do some kind of data organizations. So whatever data sets which is present in this cluttered reality-based informations, and then we select few of the information which is needed for a specific analysis, then we have to do some kind of organizations, and then based on these organized data sets, looking for few specific analysis algorithms, finally the dissemination of those results is being provided by the GIS to answer the questions which has been asked. So in between, you can also have few kind of interactions with the models to get an exact answers. For example, you want to find out path from location A to location B, so it will give you a specific path considering or giving the what is the total time which you should take. But it also gives you few of the other alternate routes. You can select them. You can also come get some additional information. So those are the additional interactions that goes during the GIS processings to do a re-representation of the output so that the users can understand what are the different scenarios under which these results are being generated. So current lectures, we are restricting ourselves just to data organization sections, and that's data organizations we are going to take forward in GIS world. So as we have seen in the previous example, so let's dissect the informations which is required to solve the problem for reaching from place A to place B. So if I just ask anyone who is not familiar with GIS or maybe anyone on the road, and you just ask them, any old person or person who is living in nearby areas, that you want to go from place A to place B, that is from IIRS to clock tower. So with his or her experience, he will know, okay, what is the meaning of IIRS, what IIRS represents, which place is called clock tower, and he will also having some experience that how you can reach from clock tower from IIRS to a clock tower. So in between, he'll be saying, okay, you need to take basically a route from Kalidas Road, which is present, which is actually the place where IIRS is present, or the nearest connectivity to IIRS is present. And then he will talk about that you need to just take a connected road which is called Rajpur Road, take a right turn and go move straight, and you'll be able to reach to clock tower. So in this case, the information which is required to solve this particular answers to these questions is just based on the information which is present in human mind or with the human experience. So at the end, he will just say that from Kaldas or from IIRS to Kaldas or to clock tower, you can go via Kaldas road, and then you can reach to a Rajput on a Rajput road. You can reach to a clock towers. So someone may also give you some additional information that generally it takes 8 to 20 minutes depending upon the traffic which is present on the road. So this is completely human based interaction which you can query or ask anyone who is present in nearby areas. But what about if we want to have these particular answers from a systems or like using your mobile phones? So in that case, whatever the human information or analysis which was we saw in earlier slide, that needs to be first converted into machine readable or machine understandable data formats. So for that, we have to do a kind of categorization of the information. So in this case, for example, place A, which is IIRS, is actually a point locations. So that is called a point geometry. Similarly, the B is also a point geometry, and or both of them will be having some kind of locations which is marked in latitude and longitude formats. Then once we have these location points from what is the starting point and ending point, then we have some additional informations which is nearest to these locations. Those are actually road. So roads are actually being represented as a line geometry, and it has some additional attributes like its names, for example, New Kent Road, Rajpur Road, etc. And sometimes what may happen is, in general, whenever we say line or segments in general terms, in case of GIS world, there may be a set of or a set of continuous line segment, which we call it as a line geometry. Then apart from these geometrical properties, there will be some additional informations like how much does it time takes from each of the road segments, like how much time if I take an entry point from any place in New Kent Road to go to a Rajpur Road, that particular sector or that particular section, how much time does it take? That can also be stored so that at the end of the analysis, the actual time which will be taken can also be displayed to the or can be provided to the end users. So such additional information which is related to any kind of geometrical data sets are called attribute data. So these basic understanding that any kind of spatial informations are actually will have some kind of points, locations, or maybe a line segments, and so to solve this problem, along with the additional attribute informations, we organize all of them so that we can carry out the analysis that how much time does it takes. So in general, the machine data, whenever we are saying, so machine data is actually a geometrical properties or the locations or the point locations. It's in a particular coordinate reference systems along with the geometrical representation like point, line, polygon. And then we add an additional attribute which is required for any kind of analysis that combined together is being represented in a machine data format so that we can use them to find out a very simple solutions like finding a path location from place A, that is clock IIRS, to B, that is clock tower. So this is basically the reorganization of the whatever human information was there that got categorized, grouped together, and in general those are called point and attribute informations. So if I say this, if I do a representation of these data sets, so in general, the GIS data sets will have certain amount of attribute data, and there will be few map informations, which is nothing but a geometrical data sets. In general, the GIS data sets, the organizations of the map informations are generally grouped or put into two different larger group, which is called a vector, which is completely geometrical based systems, and along with the raster data set, which is a kind of gridded systems. So these two are basically a two-dimensional representation of information in 2D GIS analysis. I just wanted to highlight here that we are not discussing the three-dimensional representation of the GIS data models in current lectures. Then we are also having, but we can represent that 3D information even using two-dimensional data structures using TIN. So we'll just have a look of that as well. So combinations of these raster vectors and slight modified version of the 2D representations, which can be used for representing 3D surfaces, are called map datasets. Nowadays, these informations, which is attribute and the corresponding map datasets, can also be stored in certain databases, which is called geospatial databases. So in some cases, they will be very specific geospatial databases. In some other cases, there may be an existing databases which will have an additional I should say functionality, which will provide or which will convert a normal database management system into geospatial database management systems. So this basically what it requires, the geometrical representation. So generally, in general, we group or provide three larger group, that is point, line, and polygons. And these are basically based on the simplification of the representation of simplex geometry, which is nothing but point, which will just have a locations associated with that. Line will be a sequence of point in an order, and those can be called as segments. And then each of those segments, if you connect them together, you'll be having a larger line segments. If the line segments closes at the same place where it is started, then it forms a polygon. So this is how the geometrical representations in a vector format is being done. In a rasters, we'll have some other way of representing it. We'll see at later stages. Then we have an attribute data. For example, point will have a corresponding name, so that will be stored separately. And there will be a kind of references which will link the attribute and geometrical data sets. And whenever we want to have the information about any points, what it names and so on, so based on this common unique reference number, which you can consider as a key, which is being shared between geometrical and attribute data sets, that can be used for finding out different attributes of any geometrical data sets. So you can have a point with the name, the same way we can have a road name length in a case of previous requirement. Apart from that, there are certain additional information which is also present in your different machine data representations, which are called auxiliary informations, which are actually required for doing some kind of analysis, and that's being used for internal consumptions of the data sets by the machines. And it also provides some specific measurements, details, and if there are certain distortion or error is there, so we can find out based on these auxiliary information as well. So this includes the coordinate systems, there are scales at which the information is stored. The extent is also, instead of looking for whole earth while doing an analysis, extent can help us to just restrict the query or search query within a range as well. The geospatial data sets also have a very unique attribute, which is called spatial relationship, which is nothing but a kind of neighborhood relationship, which even if you do a transformation in any form, that is not going to change. So in this animation, we see that there are a piece of paper which is having a location marked ABC on the right hand side. So whatever we do a transformations of these piece of paper to just convert maybe a bird or maybe an elephant, so their relationship, or there the neighborhood relationship between point location or the any polygon part A, B, C is not going to change. So this property of an objects which is not going to change during any kind of transformation, so that can be a transformation from 2 dimensions to 3 dimensions, still gets preserved, and that's possible through the on the basis of topological relationships. So in general, it's being just defined as that it's basically an invariant relationship which under any kind of transformations remains static, or that relationship is not going to change. So those transformations may be scaling. So if you just stretch this, just think of this, instead of having a paper, it may be a kind of rubber sheets. So if you're having this rubber piece of a rubber sheet, and if you just try to expand it, again the neighborhood relationship between AB is not going to change. So it means if you do some kind of scaling, rotating, or transformations, all those mathematical operations, it is not going to change. Then there are also a directional properties. For example, if I want to say what is north, what is south, which particular piece of polygon is north to which one, and so on, these kind of spatial relationship can also be is not going to change. Then in reality, there are few metric relationship, like whatever you do, the distance between two places is not going to change. So that's the how the in real world. In a representations, there might be some certain issues, but in real world, those metrics is not going to represent. So these kind of spatial relationship, which is invariant, or which is, should not be changing in any conditions during the transformations, that properties also needs to be preserved whenever you are organizing any kind of spatial data sets. So considering all those facts, there are some additional consideration which we also need to take into, that whenever we say spatial informations, we talk about the spatial information which is present in 3D world. So we may be representing these information in a 2D domain, but actually these informations comes from the 3D world, which is nothing but on Earth. And as you can see that the shape of the earth is not the sphere, or it is not even a regular spheroid, but it's a kind of it's nearby to spheroid shape. So what it means is it is not exactly the mathematical representations or common notions which we have that earth is actually a sphere. That is not the case. So if you want to represent these spatial informations, you need to look for some way so that these information which is present in uneven shape of the earth, that can be represented and will have a unique references on 2D representations. So while doing that, there are two steps process. So generally what people do is that they take this irregular shape and try to get an approximate theoretical 3D spheroid, which we call it datums. So generally we define an datum, so that datums can be based on local demand, or it can be a global demands, and so on. So that basically approximates this shape, so that wherever we want to find out or do some kind of measure distance on these particular reference systems, it should not differ much in reality. Then once we have this geometrical approximation of the shape of the earth, then we need to represent them in a 2D world or in a form of maps. Since we are talking about the two-dimensional analysis, so finally these 3D world datasets has to be represented in 2D maps. So what happens is that whenever we try to represent any kind of two-dimensional three-dimensional data sets on 2D plane, so there are bound to have certain amount of distortions. So it's always an individuals who want to do these kind of transformations, they need to make certain choices. So those choices are there. If you try to represent any three-dimensional spheroid on a two-dimensional paper sheets, then there may be a distortion which may include a shape in distortions, or the distances which we measure. For example, the latitude distances which is present at equator will be quite different which is present at the pole, because in the pole the latitude distances, or the distances, or the between the 2 points on latitude, on the same latitude, will be different, because the circle size gets decreased as you move from equator to polar regions. Same way, if you do a transformations, then the angular angle between 2 points gets changed. So means there will be a directional representations which will get affected if you do a 2D projections of 3D data sets. There are also a possibility of shape distortion, so means any features which may look smaller on the 3D world, but if you just try to represent in a 2D world, then it will get exaggerated. For example, in the same animations, if you see that if you go for basically a cylindrical projections, so what happens is that at the equator, at the polar region, the area which gets depicted seems to be quite exaggerated compared to the real world. So this kind of deformation is possible whenever we do or whenever we try to represent a 3D domain to 2D domains. So we have to fix based on certain compromise that what is basically our objective and analysis requirement, and accordingly we select the accepted compromise representation of these three data sets in 2D world, that we call it the spatial referencing systems. So once we decide these spatial referencing systems, then we do a reprojections of those information in 2D series or 2D planes. And finally, we assign a coordinate systems which says that what is the origin, what is the start point and end point based on local referencing systems, so that a complete GIS spatial referencing system is built. And on this referencing systems, then you start representing all those geometrical property, that is point, line, polygon, and so on. So let's have a few also look into some spatial relationship, or especially the topological relationship. For example, there are certain states which is on the north or south of some other state, that particular relationship is not going to change even if you do transformations in which shape may be distorted or the distances may be exaggerated, but in general their attribute or the distance or the north and south positions, those the state those kind of relationship is not going to change. For example, the Uttar Pradesh is actually to north to the MP. So this Madhya Pradesh. So it means like it is not going to change even if you distort it, make some changes, and do some kind of transformation. So this particular topological relationship may also require to be preserved in some cases. So especially there might be a certain GIS analysis where this spatial relationship needs to be preserved. For example, we may have a query like how many states are bordering the Madhya Pradesh, or what are the different state which is surrounding the Meghalaya. So something like these queries can be answered only when you know what are the different states which is surrounding the state like Meghalaya or any other states. So for this spatial relationship also needs to be represented in some cases, and then there, so that in some cases the metric distance also needs to be preserved. So this spatial relationship also needs to be preserved in along with those spatial references and their representations. So there are certain basic representation of spatial relationship. So generally it can be categorized in 8 different spatial relationship if you look into closely. So it's measure we can divide it again into 4 measure group, that is the disjoint, meet, equal, and inside. So what it means is that there are certain polygons or a point which is having no common point, those are called disjoint. Or there may be a certain sections which is just common at the border, which is we call it as a meet. Then equal is if one particular spatial feature is exactly covering the other features, and in some cases we may have one polygon which is completely inside. So let's view example of that. So let's say we are having in India, and then we are also having a for example any other country which is distant one, that is Afghanistan or maybe UAE. So in that case, the polygon or the shape of the India is not exactly adjacent to UAE, but it's a kind of disjoint. Similarly, if I take two state, for example, Bihar or Uttar Pradesh, so then there will be a few bordering areas where both of them will be sharing the boundaries. So that is the relationship which is existing between polygon of Bihar and Uttar Pradesh is called meeting relationship. In some cases, you may have a completely cover. For example, if I take all the states of India and we just overlay the shape of India on the all the states of the India, then what will happen is the outer boundary will exactly match with the state boundaries, and as a whole, they will be completely equal. So those are called the equal relationship. We may also say that, for example, the Madhya Pradesh is completely inside the India boundary. So it means it is sharing no international borders with any of the neighboring countries. So if you just, so these are the basic four relationships. So there are also a viewpoint, which is just taking opposite of that. For example, A is covered by B. So in this case, that blue polygon is covered by the red polygon, or that we can also say in the reverse is that blue polygon contains the red polygon. So it means that it's a perspective in which this spatial relationship is being represented. So these spatial relationship also needs to be preserved as a part of few GIS analysis which is required, and the corresponding data structures also needs to take care of that. So in general, there are certain phenomenons, a spatial phenomenon which is discrete. For example, roads, which is very unique. They will be having exact boundaries and they will be very distinct. Similarly, the district boundaries will be distinct. It's a kind of polygon areas and will have a very clear distinct boundaries. Then there are also certain phenomenon or representation which is continuous in nature. For example, terrain or temperature. So it is, you cannot just say that from this boundary onwards the temperature is going to increase and this is the exact end point where the boundary, the temperature will be different, because the terrain, temperature, all these geographical phenomena are continuous in representations. So means we need a separate way of representing them, and generally those are being represented in a continuous field-based data structure that is called a raster. Then we have another basically a polygon based representation, especially spread but still continuous. That is the land cover, but there will be a crisp boundaries in general in representation of the maps and so on. So it means there are certain phenomenon which is discrete, there are certain phenomenon which is continuous in nature. Some of these discrete features will have very crisp boundaries, and continuous phenomenon system will have no such crisp boundary present. So once we understand the different spatial phenomenon and what are their requirements to be for representation, so that we can do an analysis. So let's look into a few basic data structures which is being used. So most of these data structure, the initially one was the vector data structure. This is the basically an abstract models. We'll look into physical representation at later stage. So in this case, as you can see, we are having a spatial referencing systems, which as we discussed earlier, that can be based on the certain projection systems, origin, and accordingly you'll be having a coordinate system presented. So in this case, we are representing this, and this is being marked. So each of those lines are actually being marked as a unit discrete points. But any feature or any point which has to be presented in this two-dimensional reference plane can have fractional components. For example, if you take a point 1 which is marked at the bottom left side, so it is having a certain position which is not exactly starting at a location 1, but rather than slightly shifted towards right side. So we can call it, this position is actually 1.12 or 0.1 depending upon the scale which you think, and it will have its corresponding x positions. Same is that case for the y presentations. So in this case, we see that each of the point is actually having a fractional representations, not very discrete or integer representation. So any real value can be represented for giving the positions of a point. So if I want to make any kind of line, so what I'll do is I'll take each of the point which is present in my region, and I'll just represent all of their locations in x and y location format, and then I'll just find a set of sequence of point which if I traverse in a linear directions, then I'll be able to form a line. So for example, the line number 1, which is at the bottom, is consist of point 1 and it is ending at point 4. In between you're having two additional point which is called point 2 and point 3. So in that case, the line 1 is actually representing 4 different points, and those points needs to be traversed in an order. So if I have to maintain a topological relationship, then in that case I have to also define which is the start point and end point. So in this case the beginning node is 1 and the end point is 2. So that way we can represent our line. So as I said earlier, that the polygon is nothing but a closed line. So in this case, if I want to represent a polygon PL1, which is actually the combination, or which is basically a closed representation of the line segment point number 2, 3 and 4, if I combine together, so you'll be having that red polygon which is being shown in this case. So that can be represented and we can put it in a polygon organization. So this way we are having a set of a representation of these points, their connections and their organizations in a theoretical way, and this tabular structures is basically the basis of any vector data representations. In case of referencing systems, the spatial data sets can also be represented in a tin format, and which can also be a part of any GIS data sets, which is the three-dimensional data sets, and will have a kind of referencing systems. So considering all those representations, the basic representation model of vector data sets, let's explore the very beginning or earlier representation of the different spatial models. So in this case, as you can see, there are 3 different features that is called A, B and C. A is a polygon, B is a point and C is a line. And polygon A is having again consist of the point which is 1, 2, 3, 4, 5 and 6, and we are also having lines which consist of points 7, 8, 9 and 10, and 11 is the independent point. So in this case what we do is, if this under the spaghetti model, all these 3 different phenomena are being represented in a single file. So in this case we can say polygon A is consist of 6. So A is actually comma 6, telling that there are 6 position points, and I will just be putting what is the starting point and what is their ending point, and corresponding coordinate of those points in an order. So as you can see that A comma 6 basically says that A is consist of 6 points, and all these 6 points positions or location are being followed in order. So that is 1 comma 3, 1.8 point, 2.6 is basically a second point, then 2.8 comma 3 is the third point, 3.3 is the fourth point of the polygon, 3.2 comma 5.2 is the fifth point, and 1 comma 5.2 is basically a sixth point of the polygon. So as we have said that we are going to have we are having just 6 points, so after that it ends, or any kind of systems can end, and it will know, okay, all these 6 points basically is the part of polygon A. Then we go for the next line which just says 1 comma which says B comma 1. So that basically says that B is the other features, and which is having just 1 point, which is 4 comma 4, and that's how the point is getting represented. Then we are having another feature called C comma 4, and in this case all the points of which is a part of the polygon C is being represented with all the 4 vertices in the order. So this is a very simple models. If you are not doing, or if you are not aware of any kind of GIS software or models, but still you want to organize and do some kind of representation, this spaghetti models can be used very basically, and that can be put in. So this is how the earlier representation of the vector data model started. But what happens is, in this case, there are an issue which has been arising. So what it means is, in cases where if you're having multiple polygons sharing the same points and so on, so in that case what will happen is you have to repeat the same point multiple times. So in that case there's a redundancy gets increased and so on. So to overcome that, there has been another models which we call it a dime models, which is based on the basically a vertex dictionary. So what it does is it basically creates two separate files instead of one. So one file is just a vertex file or the point location file which it contains, and second file just talks about the part of the each of the points which is part of any of the point, line and polygon geometry. So in this case there's no duplications, but there's no possibility of storing a topology. So it means like I cannot know, or I will not come to know that C is actually to the south to A or not. That particular query cannot be answered through this. So to overcome that, again at later stages, the topological relationship also been added along with this vertex dictionary and feature geometries, and those basically are being represented with its another file which is called as segments, and started telling that which of the polygon is left and right and so on. So means it gives you the each of the segments and the corresponding on segments which polygon is the left and which polygon is the right. That particular information is being represented or encoded into dual independent maps, or that is the dime format. So as a result, now we know that there are certain queries can be carried out. For example, let's say I would like to know on the left or the right side of the D, is there a space which is available, and so that I can extend the polygon A. So in this case I can do a query because I know that on the right side of the D which particular polygon is there, and this polygon is actually external polygon, not part of anyone. So it gives the kind of query result that I can do some kind of extension. So the topological relationship has started coming into the data representations. At very later stage, and which is actually most widely used in different commercial softwares in early GIS development, which is called a ARC model. We just extended it. So instead of having dime-based representation, it started sharing the 4 different files. So in that case, you'll have a node topologies, then there is a polygon topologies, then you'll be having a coordinate of the vertex, which is the left and right, and intermediate nodes. And finally, it gives also stores the arc topologies as such. So in combinations of all these data structures, the arc became a de facto model at later stages and was quite widely used for a longer duration of the time, or I should say till the advent of the geodatabases has been in wide use. Now let's come to a raster data representation. So raster data representation is being used for representing any phenomenon which is continuous in domain, or which is basically which phenomenon which is continuous in domain. So in that case, the idea is just to have a kind of gridded structures, as we can see in this case, and each of the gridded structures will have a certain number of rows and column, and the value of the phenomenon will be considered to be located at center of each of the cell which is part of this the grid structures. So the values can be put in each of these location, which is called an attribute of these data sets or these raster data set structures. And the topological relationship is inbuilt within itself. Like if I want to say, let's say, which particular shell is actually left to 3 comma 4, or the cell which is in the third row and fourth column, and I want to know which one of the other cell is which is left to it or right to it, or upside or downside, or maybe north and south to this particular cell. That can easily be found out because the structure in this case is very rigid and it is being put in. So it means like it is having a grid level structures, and each of those grid is just going to store the attribute data sets. Here one point needs to be highlighted here, that the raster data sets generally stores a single values in a single layer or a single layer, or if I say that in this gridded structure only you can store in a single values, where in the earlier vector data set, since geometrical part was separate and there was a reference link, so you can add multiple attributes and you could store it in a vector data format. But in the raster format, that's not possible. That's why you have a lot of attribute data. If you're having a raster data, then you have to deal with multi-band raster data sets. Then we are having the other thing which we need to understand is that in this case, spatial locations are fixed. There is a no intermediary location which is present, which was possible in a vector data sets. So any point which is at the center, if I want to represent any kind of the phenomenon which is just right side or the left side of the center, I have to forcefully align it to the either into center of the current cell or nearest point to the next cells and so on. The intermediate points will not be there. So this has a lot of repercussions, that the geometrical locations are fixed. Then there is a kind of geometrical error in that sense. So and so on. So those things needs to be kept in mind whenever we are doing or giving any kind of spatial accuracy related to raster data sets. Then other issue with the raster data sets is that the same polygon which was earlier having a fraction data point representations, now when we do a rasterization process, then its shapes gets varied. So as you can see, the polygon which was there, the red color which was there in the vector data format, if I convert it into a raster representations, then it is no longer the smooth surfaces or the outer boundaries is no longer the way it was looking, but rather than it has been now grid filled locations. So this basically shows that during the rasterization process, there is an induced error in measurements in terms of spatial shape or area, and as well as there might be some other error. For example, there in some cases there might be a missing grid due to rasterization process and so on. Then also one important point needs to be observed over here, that the point which is represented by a point number 10 is now going to acquire a cell, and the center of that the cell will be actually called the representing the point. So it means earlier in the 5,9, that point which was there, the point number 10, which was not exactly at the center, but now it is forcefully has been shifted towards the 1. So that's basically is the positional error is being put in. Then since the rasterization has happened, so the smoothness of all the curves also get lost. So this is just an important aspect which we need to consider whenever we are dealing with any kind of raster data sets. Then raster data sets also have a certain compression algorithms, which is just a gridded data, and then you organize them in a group. So those groups are based on the run length encoding, chain length encoding, blockchain coding, and quad tree training. So what we see is that in the first case, you just take an outer shell, and based on that you start moving, and you just say that how many cells you need to move in, that list has to be provided. So that's called a run length encoding. Chain length encoding, basically you look for an outer set of cells which represents a polygon, and that's how the chaining cells or the closed cells forms a kind of area which can be considered as a part of the polygon. In case of blockchain, what you do is you take a block by block, so those blocks are equal in length and height, and accordingly the bigger to smallest number of such cells are being selected, and that's how the block encoding works. And the quad tree is is a similar extension of the block encoding. So it just divides the total area in equal parts till it forms a homogeneous segments, and whenever it is finding any part in a homogeneous sections, it stops, and that's how the quad tree representation of the raster data can help for compressions. So let's have these few examples of the rasterization process. So as you can see in these polygons, there are a few polygons and lines are there. So whenever I carry out the rasterization, so as you can see, those roads which is present on the top as a line has now have a zagged effect, the smoothness has gone. In the meanwhile, also there are a few polygons, which is cyan color river, which is being represented in this case. So as you can see that there are certain places where in a vector format the data sets are actually having a continuity, but after rasterizations this area or this particular connectivity is lost. So this has happened because the cell within which falls under this polygon is having a lesser number of area compared to overall features, and accordingly this linear features discontinuity is being observed. So this is quite common observations whenever we do any kind of analysis where you have a vector data, especially the linear features, and you just do a rasterizations and you carry out the analysis. At that time, this missing connections, errors, which may be get introduced in your data sets, and finally that may affect at the final analysis of your result. So let's summarize the vector and raster data models. So it's basically a vector data models are object-based, very discrete, where cell is actually full area-based or field-based representation. It can be used. Their points are actually can be a fractions, where in raster cases the locations are x and y. It takes lesser space because you need to only represent those points which is a part of it. The rest of the point is not being represented, and then you're having a few in vector data. One of the important properties is that each of the point will have its referencing point, where in case of raster data, since the value is considered to be center of the cell, so it will have just an origin references, and then distances between two cell and their direction is well known. So you can simply compute the location of any grid by just adding the number of rows and column and the corresponding width of the cell to find out the georeferencing location of that point. So this gives the another very large differences, that in case of vector data each point is being referenced, where in the case of raster data you have only origin point which is being referenced, and with respect to that each of the cells location is being location is being computed. So there are a few well formats like KML, file GOT formats, and so on, which is being represented. So let's see what are those file formats are there. So in the geospatial data file formats like vector, we are having a very widely used format like GeoJSON, KML, shapefile, WKT, and all these formats are available from different sources, and they may be they all of them basically represents a vector data format. So in what it says is that the basic representation, or the at the very abstract level the representation almost remains same, but there may be certain additional functionalities can be added in these data formats. Similarly, in the case of raster, you have H3 grid, GeoTIFF, JPEG 2000, and so on. Those are the presentations of the raster data formats. Some of them follows the navigation standard formats, which again is a kind of vector data, like for example, GPS devices generally represents and complies with the navigation standards. Then there are also a geodatabases, which basically supports the different ODBC connections, and that's basically used for storing the GIS datasets. In a or remote sensing areas, basically the multispectral datasets, which is nothing but a kind of raster data format stacked together, where each of the band represents the characteristic or phenomenon which is being observed in a specific spectral band that is being stored. Same is also is the case with the lidar datasets and radar datasets as well. As the geospatial datasets is no longer just restricted to your desktop based systems, but it has also now gone into a geospatial based analysis. So accordingly, you have a few data standards which is based on OGC web standards, that is called WCS, WFS, and so on. So these data sets basically allows the representation of these geospatial data sets, which can be transformed, or which can be basically transported in a web environment from main server to the client machines. Then nowadays you're having a few the pictures which is getting collected by your Mobile cameras, it has some additional attribute which is geotagged images, where the locations is being captured by your mobile phone's GPS, and that gets stored in along with the metadata of your video, pictures, and social data sets, and so on. Then there are also 3D file formats, which is not directly as a part of GIS data sets, but is being used for, or even, which can be used for a certain amount of GIS analysis. There are also a few projects file which is not representing the data sets as such, but just having a kind of detail of the metadata which will be part of any GIS project. So let's explore few of the basic things which is present, which is being represented. So this shows the structures of basically a personal geodatabases, which is quite widely used in commercial domains. So as you can see, there are personal geodatabases which has a feature data sets consist of point, line, and polygon. So in this case, the vector data is the feature data set which contains college, LULC, and major road, which is point, line, polygon within the feature data sets. The personal geodatabases can also store the raster data sets, which is in this case the DEM or a height file, which is a raster format, is being also being stored. Then these database can also store the network data sets, which is again a kind of extension of the vector data set, but certain additional attributes which is required for conducting the network analysis. So it means like it can just do a conversion. So there are a few conversion tools are there which will allow your geospatial data sets to be converted into network data sets, and that gets represented, that can also be stored in a geodatabases. Then there are representation of the ARC file, which is part of your old standards. As we can see, the ARC node and tick file, those are actually part of the coverage features and quite widely used earlier. Then you will be having a kind of shapefiles format, which is the shapefile and corresponding additional file like attribute data sets along with the few referencing systems will be represented in your data sets. So it means like this, these are the basic logical representation of the spatial file format, which is commercially used in standard formats. Then at the back, if you go into folders or location and try to look into that area, then the same file will be seen in quite different ways. So as you can see, those shape files is no longer just attribute and shape file, but there are some additional file like PRJ, SBN, SBX, and so on. So if anyone who tells you that please provide me a shape files, you have to make sure that you are not going to only send the SHP file, but all the additional file, auxiliary information file, which is part of these files, has to be distributed. Otherwise, if the end user is just receiving the shape files and rest of the information is not present, the information or the file will not be useful. So these general common mistakes generally people makes when they just start doing GIS analysis. And if any one of his colleagues says that please provide me a shape file, so generally the only file which is having extension SHBB is being forwarded. The rest of the file is not being forwarded. Then you can see the coverage and the other databases, how it looks like. So it's like there are a lot of acronym file, and it is having an ADF extensions and RPX extension and so on. So these are the inside file or a kind of I should say the folder based file format which you see in the back. So in general, all those logical representation, if you see, the geodatabases will have a feature data sets, which will have a spatial referencing, object and subtypes, feature classes, relationship between among the classes, network topologies, planar topologies as a part of the feature data sets. Then it also have a domain and the validation rules sometime also. So if you want to carry out certain amount of topological analysis, then you can enforce that there are certain relationship which has to be preserved while adding or editing any kind of attribute. Those validation rules can be added. So those are actually a part of the set of feature data sets. Then you have a raster data sets, which is just a representation of raster like TIFF or the IMG files and so on, which can be directly stored in your geodatabases. Then geodatabase can also store the tin and few additional attribute location like locators and so on. So let's have a view of the current standards which is being now used in recent data in recent data representations. So which is based on the OGC simple feature model. So the OGC is an open geospatial consortium. So this basically objective is to standardize the representation, processing, and a lot of different geospatial analysis and techniques in a format so that the interoperability between different softwares along with the models and so on can be observed. So based on that, they publishes a lot of standard models. So they have also published one of the standard models called which is basically related to feature models. So let's have a very basic representation of that, that is called the geometrical models. So in these geometrical models, they allow nowadays not only to represent a point or line that is which has been again grouped under the curve, but now it can also define surfaces, geometrical collections. So it means like the features are no longer just needs to be a single point line polygon, but a group of those combinations can also be represented, and those are actually geometrical collections. The importance of these we'll see in coming slides. Along with those geometrical feature representation, it also stores the spatial referencing and the different type of plane geometries like point, line, strings, rings, polygons, and so on. So these are like in some cases the polygon may have inner polygons, so it's kind of there might be a hole and so on. So these data sets has to be represented. So it means like it allows to represent the different spatial data set which is found in the real world in an appropriate manner so that analysis can be carried out. Then there are also a few method or classes are being provided which ensures that the feature data sets are having a particular spatial relationship which can be used for spatial analysis. So these are the few additional OGC standards allows you, like you can have different point, line, polygon features. As we can see, those are a one multi-point. For example, there might be a set of points which is called a rest location as a group. Similarly, you can have a cycle path or department. So in such cases, the OGC calls them the multi-point, multi-line, and multi-polygon groups. Along with that, this also allows, which is homogeneous in nature, but heterogeneous data points can also be stored. For example, if you want to just define a departmental area, so which will consist of a few points, there will be few pathways, few buildings combined together, they call it a department area. So it consists of multiple multiple geometrical features, which is having a different shape files. Then in the recent time, the GeoJSON format is being used. So this just shows the representation in a text file. So as you can see that it can be simply created in a text file format, and it has a lot of attribute associated with it. So as you can see on the top, it's called the feature collection, which consists of a set of feature objects along with the attribute data and corresponding geometrical objects. Then geometrical objects allows to contain the different multi-line, multi-polygons or collections which we have just discussed, which can be put in a GeoJSON format. That's why this is being quite widely used in the recent times, because it is easier to create and it allows the representation of multiple heterogeneous geometrical objects within a same file. Along with that, this also allows certain attributes like colors, strokes, width, and so on, which can be used by the rendering engines to represent all those GeoJSON dataset format. There is also an open source GPKG format, which basically takes the inspirations from the same OGC standards, and this is now the de facto standard which is being used in open source world like QGIS. So if you want to create any kind of geospatial database, vector data sets, it will be stored in a GeoPKG format. So it's a single file format. So as I said, like earlier, the shape file was the de facto format. But as I was telling, shapefile is not a single file, but it consists of multiple files. In fact, there are 6 files which is required to define a shapefile formats. So instead of that, and as I told that there are issues of missing or deleting or missing informations during transmissions and so on. So the geospatial or the GIS, QGIS community decided to use basically an RDBMS container-based systems, which is based on small SQL file-based SQL systems that we call it a GPKG formats. So it can store the different vector and raster file formats along with a set of tile imagery and so on. So that gives the kind of quite flexibility to store the geospatial data sets and attributes which can be in binary format. For example, a point, you may be having a point locations, and at that point location you may take certain photographs, so that photographs can also be stored as an attribute within the same file structure. So that gives the kind of extra flexibility to store or manage the data set in a single file format. And that's possible because there is a blob data structures which is being stored in this data set. So this stores in a tabular structures, like it will have a few column names corresponding as RC, SRS and so on, along with the attribute which gets stored. The other widely used file format is a KML. So again, it's a very similar to GeoJSON file format. So it means like it is also having a few the completely textual representations. You can just open a text file and view it, and it has a set of point as a part of line strings. It also stores the along with the feature and geometrical objects. It can also store the ground overlaying. So means if you just take an image, on the top of that you overlay some additional annotations, so that can also be stored as a part of the KML file format. Then it has a color, style, representations and so on, which basically helps to represent it in a different file form in a different software, along with the other geometrical and other attributes parameters. Yeah, one important part also is there that in a basic KML file format, we can also use the store the time sequence. So means there might be a multiple snapshots, all of them combined together and giving you a view. So this is very nice representation in the cases where you have to store the continuous stream-like data sets. For example, if you are traveling on a bike and you are collecting data along the path, so you just want to store all of them in a single file, so that can be stored also in basic KML file format. So last, we'll just go through and see the 3D representation. So 3D representation is basically based on tin topological models, so which stores the same point and all the x and y coordinates, 2 dimensions. Along with that, each of the nodes will also have a z coordinate or the height attributes, and these height attributes are created in such a way that it's the Dulensing triangular constraint is being maintained. So what it means is that any 3 points which you take it in any upper and lower surfaces, all of them should intersect and fall on a single line. So more detail can be found on a net what exactly the Dulensing triangle is there, but in general these tin topologies are basically 2-dimensional representations which stores the height attributes, and that can be stored in a form of tin representation. So these are the few triangulated irregular network model or the tin models representations which we see in this case. The temporal representation is also possible, where multiple snapshots and multiple objects can be stored. Especially this is the another way of representing the spatio-temporal data sets in a single file with combining multiple attribute data. There are also a few representations on spatial information models, event process models. So these are very specialized models. Generally, it is not required for normal GIS representations. These are very specific requirements may be required for some process-based model which needs to be integrated into multiple systems. Recently, there has been evolutions in DBMS technologies, and big data file structure format has also come into a play. So that's again stores the GeoJSON kind of file format in a multiple segments. This is just an example of R-tree-based file systems, which is again based on the DBMS technologies and as well as file format based systems. So this is just a representation of the different attribute and data relationship which is existing between spatial and as well as the attribute data sets. So with this, we are just closing this session. So if you have any questions, please post it and we'll be happy.